All right, so 4.1 part 2 is what we're talking about. All right, so on Friday, we said that an angle in radians, so theta in radians, was equal to the ratio of the arc length to the radius. And let's, computers, let's close them, please. So what we're going to do is multiply both sides of our equation. So we said when an angle in radians is the ratio of the arc length to the radius. We're going to multiply both sides by the radius, and we get that the arc length equals r times theta. This works only when theta is in radians. So theta must be in radians. So our arc length is the radius times the angle. And when you were in geometry, you probably learned a formula for arc length where you took the angle and divided by 360 and multiplied it by the circumference of the circle to find the arc length. Basically what you were doing there is converting the angle to radians. So that's what the arc length formula that you probably learned before. You were converting the angle to radians before you found the arc length. So the kind of question that you might see with this kind of problem, I want to ask it. Do the question in the terms that the book may ask you the question. It would say find something like find the length of the arc. Subtended, or that subtends. An angle of 120 degrees in a circle with radius 5 inches. So that's a kind of question that you might be asked. And what this is asking us, so I'm going to draw a quick sketch here. There's my circle. There's my 120 degree angle. There's my 5-inch radius, and it wants to know how far is that arc length. So that's what the question is asking. What is that arc length? Well, we know that S equals r theta, but our angle has to be in radians first. So let's do our conversion. 120 degrees equals, what's our conversion from degrees to radians? Times pi over 180. And what does this come out to be? 2 pi over 3. So we have 2 pi over 3 radians. Then we multiply that by the radius. So S equals 2 pi over 3 times 5 inches. And we get 10 pi over 3 inches would be our exact arc length. So similar to what we did on Friday, just making it a little more concrete. All right, questions there? All right, the other kind of question that you might see that involves this concept. Let me I'm not going to do everything in detail, but I want to show you how you're going to set it up. So the problem is going to say something like we have two cities. One is due north of the other. And it's going to give you the latitude of each city. So one is at 78 degrees, for example, and one is at 35 degrees. And it's going to say if the radius of the Earth is 4,000 miles. I think it's about 4,000 miles. And it'll say how far apart are the cities. So what is this question asking us? We want to hand the container to the physicist. We want to turn it into a problem that's already been solved. So let me draw a picture here. So here's our Earth. Here's the equator. Here's one city, and here's the other city, and they're due north of each other. Well, I'm going to take this and rotate it around, so we're just looking at where these cities are on the Earth edge on. So I'm going to rotate. Here's one city. Due north is towards the North Pole. Here's the other city. Here's the radius of the Earth. Here's the radius of the Earth. So looking at that picture, what is the distance between the cities? What is it asking for? The arc length. This is the arc length. So this problem is an arc length problem. So the radius of the Earth is 4,000 miles. The distance between the cities is the arc length. And it said, say it gives you the two angles, the two latitudes of 78 and 35. How do you find the angle between the cities? What did someone said it? Subtract. Subtract one from the other, and that gives you the angle between the cities. Saying one of these angles is one measure and the other is another measure, so the angle between them is the difference. We subtract. So we subtract to find the angle. So we subtract to find that theta. So don't let a problem like this trick you. It's really nothing more complicated than the last example we did. Just a little different. Takes a little bit more to set it up. Okay. Next thing we want to talk about is angular speed. The book calls this angular velocity. I'm going to call it angular speed just to be a little more precise, because we'll talk about the difference between speed and velocity. It'll be important a little later. Does anybody, physics people, what's the difference between speed and velocity? Direction. Velocity has a direction, and we're not talking about direction today. We just want to know how big it is. Angular speed is just one way of measuring how fast something turns. We want to know how quickly the angle is changing in time. So let's start with our arc length equation. We said that S equals R theta. I'm going to divide both sides by some time. We want to figure out how it's changing in time. So we divide by time t. So S over t equals R. Our radius isn't changing. We're talking about a circle. So theta over t. Theta, as if we're turning in the circle, the angle is changing in time. What is distance divided by time? What is it? Someone said it? Speed. Distance divided by time is speed, or sometimes we call it rate. We call this the linear speed. And this theta divided by time is angular speed. So the linear speed is how many inches per second, how many miles per hour is something on the edge of that circle moving. So if your car is moving forward, your bicycle is moving forward, whatever, 25 miles an hour, that point on the edge of the wheel is moving at 25 miles an hour. The way we write this is, instead of S over T, we call it V equals R omega. V is our linear speed. And omega is angular speed. So this is going to be our important equation for angular speed. And it comes from our arc length equation. We just divide both sides by the time that we're talking about. Our units for linear speed are going to be something like miles per hour, inches per second, feet per second. Angular speed, omega, our units for angular speed are in radians per time. So radians per second, radians per minute, something like that. And V is going to be distance or length per time. So we have two basic equations that we're working with today, our arc length equation and our angular speed equation. And the book calls this linear velocity and angular velocity. So speed and velocity, they kind of use interchangeably. All right, are we good with where this comes from? All right, let's look at an example of working with this equation. So let's say we have a circular saw. And our circular saw rotates at 2400 RPM. We want the angular and linear speed of the tip of the blade if our radius is 4 inches. We have this 4-inch circular saw blade rotating at 2400 RPMs, and we want angular and linear speed, and we want our units to be radians per second and inches per second. So the problem wants us to find it in these files. Often in linear and angular speed questions, what is challenging is not the concept, but unit conversions. So we need to keep track of our unit conversions. 2400 RPM. What does RPM mean? Rotations per minute. So what I suggest you do is always write your units as a fraction. I'm going to say rev for revolutions per minute. Now we would get our units canceling out right. Well, first off, let's convert from revolutions to radians. Our angular speed is in radians per time, so let's convert to radians first. How am I going to convert from revolutions to radians?
Is it just 2 pi?
2 pi radians per revolution. So let's multiply by 2 pi radians per revolution. So if we write your units as a fraction, then you cancel these out. We don't want revolution in our answer. So we get 4,800 pi radians per minute. We want our answer in radians per second. So what's our conversion here? 1 minute per 60 seconds. Our minutes cancel. And we get 80 pi omega, our angular speed, equals 80 pi radians per second. That would be our angular speed in radians per second, 80 pi. And then our equation tells us to find the linear speed from this. What do I do? We go back. V equals R times omega. We found omega, so we multiply by our radius. V equals 4 inches times 80 pi radian per second. And I get, for my linear speed, 320 pi. Inches per second. And I can drop this unit of radians because we said that radians were arc length over radius. It doesn't have any units. The units cancel out, so we can ignore the units of radians. So often you'll hear your angular speed as just 80 pi per second. You don't even refer to the radians because it's unitless. That's one nice thing about working with radians. If I multiply this out, I get approximately 1,005 inches per second. So that would be my linear speed. So that little 4-inch circular saw blade is moving. The tip of that blade is moving pretty quickly. All right. So in these kinds of problems, unit conversion sometimes is where people get tripped up. Questions on that example? Okay, so if we had a car, if our car is traveling 65 miles an hour and it says the radius of the tire is 16 inches, 65 miles an hour is linear speed or angular speed? Linear speed. The car is moving 65 miles an hour, that's going to be your V. And the question might ask you to find how quickly the wheels are turning in revolutions per minute. So we would use our formula to get our angular speed, and then use this conversion, 2 pi radians in 1 revolution, to convert that. How many feet in a mile? 5280. How many seconds in an hour? 3,600 seconds in an hour. So those two conversions come up sometimes in this problem, just for your unit conversions. All right, we good there? So I'm not really adding a lot to what we did on Friday, just extending it a little bit, adding one little concept. Okay. There you go.